Unit 14A will be our introduction to geometric optics. Geometric optics will cover how lenses work and how they're able to bend light to create an image. Many optical instruments use lenses like cameras, telescopes, magnifying glasses. Even your own eye has a lens that bends light toward your retina. Specifically, we will cover converging lenses in this unit. Converging lenses, or a convex lens, is a lens that is thicker in the middle and thinner on the edges. So this football-like shape here is a converging lens. And a converging lens will focus light rays that are coming into it toward the focal point of the lens. This is ultimately a result of refraction because the index of refraction of the glass in the lens is greater than that of air, causing light to bend. And in fact, when the light enters this lens, on one side of the lens, there's one refraction event, and on the other end of the lens, there's another refraction event, which ultimately causes all parallel light rays to be bent toward the focal point of the lens. We define the focal point as the point where parallel light rays will be bent toward as they enter a lens. And the focal point has a focal length, f, that we will use to denote the distance of the focal point. And so this focal length, f, is measured in meters. And we have our first equation for the unit, which talks about optical power. This tells you basically how strong a lens is and how it will be able to bend light greater or less. So the power equation is just 1 over the focal length. So the greater the focal length, the lower the power is, and the lower the focal length, the greater the power is. And power is measured in units of diopters. This power measurement of a lens is actually what you get when you get an eyeglasses prescription. Maybe your prescription is plus 0.5, plus 0.5. That number that you're seeing there is power. And of course, just like we learned in the refraction unit, light rays could either enter from one side or the other side, but regardless, they will still bend the same way. Refraction events are perfectly reversible. Our diagrammatic model for this unit is a ray tracing diagram, which is what we will use to determine how an object will create an image as light passes through the lens. When drawing these ray tracing diagrams, we call the principal axis the one that runs perpendicular to the lens, and the lens axis as the axis that goes through the lens itself. To draw a ray tracing diagram, you'll want to start by drawing your principal axis and your lens axis, and then drawing some object. Light will be coming from this object, entering through the lens, and passing in order to create an image on the other side. So, to draw a ray tracing diagram, you need 3 light rays to come from this object over here. The first one is called the P ray. It enters parallel to the principal axis and then exits the lens passing through the focal point. The next light ray is the C ray. It travels from the object through the center of the lens and is completely unbent as it passes through the center, so it just makes it to the other side. The last light ray is the F ray. This one goes through the focal point on the near side of the lens and passes through the lens such that it exits parallel. And now when we have all 3 of these rays converging onto the other side, we can see that the top of this person's head, the light coming from the top of this person's head, will form an image on the other side of the lens such that the image is upside down or inverted and shrunken. These ray tracing diagrams are very useful because they allow us to extract usable, measurable variables from our situation. For example, DO is the distance of the object from the lens, DI is the distance of the image from the lens, HO is the height of the object, HI is the height of the image, and of course F is your focal point or focal length for the lens. If we know the focal length of our lens and we know the distance that an object is placed from the lens, we can solve for the distance that the image will form at using this thin lens equation. Furthermore, we can calculate how much magnification the lens has by comparing how large the image height is versus how large the object height is. Another version of this magnification equation uses the distance of the image divided by the distance of the object, but it's got a negative sign in here. A negative magnification would mean that the image was inverted or upside down. So as these light rays pass through a lens, they will be directed toward a focal point, and if there's a screen on the other end of the lens, these light rays will form an image on that screen. And in fact, we call that a real image because it can be projected onto a screen. The light rays are going there in reality. So for example, real images are formed by your eye or a camera, because a camera has film that catches the light rays, and your eye has a retina that catches the light rays, and these form real images. On the other hand, it is also possible to form a virtual image, an image of something that is not actually there. And this is a very special situation depending on certain circumstances about where you put your object in comparison to your lens and its focal length. With a virtual image, light rays appear to be coming from the other side of the lens, but they actually are not. If we were to place a screen on the other side of this lens, we would realize that this person's eye was not actually there, and in fact something special is going on. So both of these situations at the bottom show virtual images. These light rays cannot actually be projected onto a screen to form an image. For converging lenses, a virtual image will form whenever the object is in front of the focal point. In this situation, the P ray is still drawn just the same. It enters parallel and leaves through the focal point. With the C ray, it's still the same. It passes through the center of the lens and goes through unbent. And if we were to draw the F ray, we would have to draw a light ray passing through the focal point, past the top of the object, entering into the lens and exiting parallel. If we were to do that, we would notice that our light rays never actually converge on the right side of the lens. But if we trace the light rays back with a virtual ray, as if light was coming from that area, then we would see that all of our virtual rays do converge at one point on the same side of the lens as the object. And this dashed object right here would be considered a virtual image because it's not actually an image that is there, but it's as if light rays are coming from that location and entering the lens. So virtual images can be a little bit difficult to wrap your head around. Hopefully we'll be able to address this in class. We haven't even covered the idea of diverging lenses, which is basically the opposite shape of a converging lens, or mirrors and how mirrors are used to form images. So more to come. That'll cover everything for Unit 14A. I'll see you in the next one.